All right. Hello, everyone. I would like to welcome you to another discussion on equilibrium stage processes, and I think it is time so we can start. I had received some of the questions regarding the examination in this course, so I will come back on that question. And maybe if some of you have any questions regarding the examination, that I will try to answer in the end. So today I'm going to discuss equilibrium stage processes, and I hope that all of you have watched a small video on equilibrium stage processes. There will be no assignment in this equilibrium stage processes, but the reason of including this important topic in this course is that you understand about equilibrium, you understand about how we use equilibrium in stage processes in separation technologies. You might have seen stages in gas absorption. You might have seen stages in the leaching process. Uh, Tomorrow we are going to discuss distillation, which is also a stage process. So it's very important for you to understand what do we mean by equilibrium stage processes and what do we mean by cascade processes, right? So I will go very briefly about equilibrium stage processes. And the main learning outcome from this discussion is that we will try to develop our knowledge on equilibrium conditions and cascade systems. I will very briefly discuss the equilibrium for stage processes in the case of distillation column. You have already discussed the equilibrium for leaching processes, and I will show you that how we can perform the material and energy balances in stage systems. And it is very important for you to learn about the concept of operating an equilibrium line. What information do we get from operating lines, right? Uh, how we can present the operating line in the graph for equilibrium curve. And I will very briefly discuss what do we mean by an ideal stage and how we can determine ideal stages. the the main application of equilibrium stage processes we will discuss tomorrow when we will discuss distillation process, but this is the main idea, is that you understand about equilibrium conditions when the streams enter to a stage and when the streams they leave a particular stage. So what do we mean by equilibrium? So if you look at this picture, you can see there is bulk of liquid and there is bulk of vapors. So we have two components, A and B. So what is happening in normal condition, that there is some evaporation. So some of the water is vaporizing, like liquid molecules are continuously converting into vapors, and within those temperature and pressure, some of those vapors they condense back in order to produce liquid, right? So if we do not have an equilibrium within this kind of a system, the liquid and vapor can have different pressures, they can have different temperature, they can have different mole fractions, right? But if there is an achievement, if there is a formation of equilibrium, the rate of vaporization for those species will be equal to the rate of condensation. So the component A that is evaporating, it will be equal to the rate when it is decondensing, and it is similar for component B. So in this kind of situations, the temperature, pressures, and the mole fractions of two components, they cease to change. They do not change anymore, right? And this is the point that we would like to reach in equilibrium stage processes, because when we achieve the equilibrium, then there is no further driving force left. So we try to achieve to a certain point, so that in the beginning of the process we have a good driving force, we have a significant amount of driving force. But when we leave, when those streams leave a stage, they should be narrowed down, their mole fraction should be narrowed down, so that they can achieve close to the equilibrium conditions, right? So in equilibrium, rate at which each species condense will be equal to rate at which evaporates. So in this case of equilibrium will be achieved, and there will be no further change in temperature, pressure, or composition. And Normally, when we have equilibrium stage operations, they are based on the principle of phase equilibrium. So when we say phase equilibrium, it means if the liquid is converting from the liquid phase to the vapor phase, it will be equal to the rate at which vapor phase is converting back to the liquid phase. So they should have phase equilibrium. And when we put all those stages, all those steps, all those plates, all those columns, packings, when we put them like close to each other, we put them integrated system. So we have cascade systems. So in this kind of stage systems or cascade systems, there will be materials flowing either in the same direction, which we call them co-current flow, or if we have the two streams, they are moving in the opposite direction, right? So the vapors are moving in one direction, the liquid phase is moving in the other direction. This is normally the case in distillation processes. So in cascade systems, two streams move in multi-stage systems and they need to be brought in contact with each other. We try to have a good mixing of the vapor and the liquid phase so that we can have a good separation. So it is very important either in the humidification system, in leaching system, in liquid extraction, mechanical separation, or distillation or drying. So it's very important that we have the vapor and the liquid phase. They should be in contact quite evenly and they are mixed quite evenly so that we can achieve a good separation. This is just to show you a stage contact for distillation process. So this is a very simple construction of a distillation process. So in this kind of system, we enter a feed into a certain plate within the distillation column. And the location of the feed, that like for example, are we going to put our feed on this plate or on this plate or on this plate or maybe upper, how we can decide on which stage or which plate we are going to introduce our feed. I will discuss that part in the next discussion on distillation about the feed quality, right? So we enter our feed in certain part of the distillation column, and then normally we have two component. Like let's say if we have a binary mixture which has two components, so one of the component might be more volatile than the other component. So when we say volatile, it means the boiling point of that particular component is quite low as compared to the other one. Like if you take an example of ethanol and water mixture, so when we put ethanol and water together and make a solution or make a mixture, ethanol has different volatility, water has different volatility. Ethanol is more volatile as compared to water. So when we heat up that kind of a mixture, you will find that there will be more formation of vapors of ethanol as compared to water, right? So because the boiling point of the ethanol is much lesser than the boiling point of the water. So we achieve two products. One is the overhead product, or sometimes we can call it as distillate. And then we have a bottom product. So the overhead product is the one which contains more concentration of more volatile component. And in the bottom product, we have component which is less volatile or which is a heavy component. Then we normally have vapors that are leaving the evaporator. So they are in the gas phase or in the vapor phase. So first we use condenser. So we take out heat from those vapors and convert the vapors into the liquid phase. And then when we take out the liquid phase, some of the material we take out as a product or as an overhead product or a distillate. But some of the material that we have to send back to the distillation column, and this is called reflux. And the reason of sending this kind of material back to the column, because if we do not send that material back, the upper plates which are above the feed plate, they will just get dry because they will not have any liquid. But if there is no liquid in contact with the vapors, there will be no separation and the vapor will keep on going and we cannot achieve high purity. So in order to achieve high purity of the more volatile component, it is very important that we return some of the overhead product back to the distillation column. And this is called reflux. and the ratio of the how much amount that we return to the overhead product is called as the reflux ratio, right? So in these kind of distillation column, the vapors move upward and the liquid move downward. So they are in counter current flow. The liquid moves in the downwards way, and the vapor move upwards. And we also need to use a reboiler, and this reboiler is a component that we use in distillation in order to increase the temperature of the liquid mixture. So we increase the temperature, so we have high concentration of the liquid here, and the vapor keeps on moving upwards, and with the reflux we achieve certain amount of liquid within the operating plate. So the part which is above the feed plate is known as the rectifying section, and the sections which are below the feed plate, it is called the stripping section. This picture is just to show you that what normally happens at each plate. So if we have two plates, so there will be liquid over the plate. Normally in the distillation we use sieve plate. Normally these sieve plates have perforated plates, and they have some holes inside the plate. So the vapors, they pass through these holes, and the vapor pressure, the pressure of the vapors, they keep the liquid flowing. So there is no liquid falling down through these holes. So the pressure of the vapors, they keep the water, or they keep the liquid stable over the plate, and the liquid falls through overflowing on the side. So the liquid flow like from the side of the plate. Sometimes it happens that if the pressure of the vapor is not that much, if it is low, so what will happen, the liquid will also flow from these holes, and normally this phenomena is called weeping. So we call it like there is weeping in the distillation column. It means the vapor pressure is not much in order to hold the liquid over the plate, and the liquid is not flowing, overflowing the side of the plate, but it is going through the holes of the plate, right? But this is one of the problem that we normally face in distillation column. But in ideal stage, the vapors, they have enough pressure to hold the liquid over the plate, so that there is no liquid flowing through the holes within the C plate. So this is just to show you that what happens at each individual stage or each individual plate in the distillation column. This is also to show you a counter current leaching plant where the materials or the two phases are moving in the opposite direction. You have already worked with the leaching, so I will not go into details about the leaching. Now there is one important question comes to our mind when we plan to work with stage systems or equilibrium stage systems. So the first part is that how we number the stages, right? How we know what is the name of the plate, what is the size of the plate, what is the efficiency of the plate. So it is very important that we first name our stages, we name our plates, right? So there are different ways that how you can write the plate number. Sometimes it happens that you can start from top to bottom, so you just put a plate number one, which is at the top of the distillation column, number two, the second, third, fourth, and so on, and plate number n, which is the bottom plate. There are some ways, like some people, they do it like this, they start from bottom to top. So they put name plate number one, which is at the lowest part of the distillation column or any equilibrium stage system, and they put plate number n at the top of the distillation column or any equilibrium stage system. But normally the most accepted way of numbering the stages is a way that we number our stages in a way of the flow of the liquid. So if the liquid is moving from bottom to top, we start from the bottom. And if the liquid is flowing from the top, then we start numbering our plates at the top of the equilibrium stage system. Normally, it is the case in absorption. It is the same case in distillation, that we have the liquid which is moving from top to bottom. So we put our plate number one as at the top, and we keep numbering plate 1, plate 2, plate 3, and so on, right? So this is the way that how we number stages. We normally name the number of stages in terms of the location or the flow of the liquid within the equilibrium stage system. The second question is that how we can designate the streams and their concentrations. So if you just concentrate on this one plate, how we can name the streams. So let's say if this plate is called plate like small n, and there will be two streams that will be entering the plate, and there will be two streams that are going to leave the plate. There will be vapors phase that is coming towards the plate N, and there will be liquid phase that is entering towards the plate N. So let's say that the vapors are coming from the bottom and it must have like vapors. So how we can name that stream? So we name V as vapors, and since it is coming from the plate N plus 1, so we name it as Vn plus 1. And what will be the concentration of the mole volatile component in this vapor phase? So we name the vapor phase or the mole fraction of the more volatile component. We name it in terms of Y for vapor phase. So it means the mole fraction of the more volatile component coming from the plate N plus 1 will be Yn plus 1. So this is for the vapors that are coming from plate N plus 1, and it is entering towards this plate N. There will be one liquid which is also coming to plate N, and it will be coming from the top plate or above plate. So we name the liquid phase in terms of L. So since this liquid phase is entering from N minus 1 plate, so it means it will be Ln minus 1. And we do denote the mole fraction of that particular component in the liquid phase as X. So we can call it Xn minus 1. So this will be the liquid that is entering to the plate N, and this will be the vapor that is entering to the plate N. Now, when there is mixing, when there is enough contact between the vapor and the liquid phase, then again the vapors will be moving from this plate. So they will be going upwards and the liquid from this plate going downwards. So we name it as Vn because it is coming from plate N, and we have Yn, which is the mole fraction of the more volatile component in the vapor phase, and it is coming from the plate N. Similarly, we can name the liquid phase as well. One thing that you really need to understand, that there are very important thing that you need to understand. One thing is that the the streams that are entering to the plate N, so it will be Vn plus 1 or Ln minus 1. So they are coming into the contact with each other on plate N. When these streams are entering towards any stage or any plate, they must not be in equilibrium, because if they are in equilibrium, there is no driving force for the mass transfer, there is no driving force for the heat transfer. So these two streams which are entering to the plate N, they should not be in equilibrium, so they should have enough driving force. But for an ideal stage, when we say that this stage or this particular plate is ideal, the streams which are leaving the plate, so Vn and Ln, so these two streams, they should be in equilibrium. Then we can call it as a ideal stage or equilibrium stage, or we can call it as ideal plate. So this is very important. The streams which are entering to a particular stage, they should not be in equilibrium. But for an ideal stage and for ideal plate, the streams which are leaving the particular stage or a particular plate, they should be in equilibrium in order for us to call it as a ideal stage. And I think you have already worked with the material and enthalpy balances in the gas absorption. So I think this is the same way that you do the total material balance and also the energy balance around this particular equilibrium stage system, right? So I think you can perform these enthalpy and energy balance, enthalpy and material balance by yourself, right? So now I would like to come to a point about what does an operating line in mass transfer mean? What information do we get from operating line? What information do we get from equilibrium line? So it is very important for you because you might have worked with operating line, that how to draw an operating line, how to draw an equilibrium line. But it is very important for you to understand that what information do we get from these operating lines, what information do we get from equilibrium lines. So equilibrium line is uh, is the one, or is a curve that gives us information about a relationship between a particular component in the liquid phase, and when it is in an equilibrium, what will be the mole fraction of that component in the vapor phase. So it gives us information about either more volatile component or a less volatile component. If the system is in an equilibrium, if we know that there is a particular value of x, which is the mole fraction of that component in the liquid phase, we can calculate the mole fraction of that component in the vapor phase. So this is equilibrium line. Normally we get the data for equilibrium line is from experiments. We do experiments and we calculate the numbers, that at what temperature and pressure those two components are in equilibrium, right? So we know for benzene toluene mixture, we can find for ethanol water mixture, we know the equilibrium data for methanol water system, ethanol methanol system. So many different types of binary system, we know the equilibrium data, right? Then again, we have to think about what information do we get from the operating line. If we take an example of distillation, operating line helps us in finding the composition of more volatile component in the vapor and the liquid phase at any point within the distillation column. So these are the actual conditions of the system, that when we know that what will be the composition of more volatile component in vapor, and what will be the composition of more volatile component in the liquid phase. And similarly, we can also show the operating lines for less volatile component as well. But mostly we work with one component, and that we use as more volatile component, right? So one important thing is understanding about the driving forces within the distillation, or in gas absorption, in leaching, or in many types of equilibrium stage systems. You might have learned about the driving forces in mass transfer and driving forces in the heat transfer. The most important driving force in the mass transfer is the concentration gradient. If there is a large concentration gradient, it means it will be much more easy to achieve mass transfer because the driving force is high. Similarly, if what is the driving force in heat transfer? The main driving force in the heat transfer is the temperature difference. If we have two surfaces which are at very high, very temperature, which has a very high temperature difference. So one body has, like, let's say 100 degrees, another body is 25 degrees C. So it means there is a temperature gradient of 75 degrees C. So it means the heat will flow much more easier as compared to if the temperature difference between these two bodies is quite low. So the operating lines, the position of operating lines helps us in finding the information about the driving force. So the distance between operating line and the equilibrium curve, it gives us information about the driving force at various point in the distillation, in gas absorption, or in many equilibrium stage systems. And how we can calculate the slope of operating line, right? So the slope of operating line in the rectifying section, it depends on the reflux ratio. I will show you tomorrow that how you can calculate the operating line for the stripping section, operating line for the rectifying section in the distillation. And normally they are dependent on the reflux ratio. And the reflux ratio is the ratio of liquid that is returned back to the distillation column divided by the liquid removed as the overhead product, or removed as a distillate. And slope of the operating line in stripping section depends on the reboiler. So it depends on the vapor boil up ratio. Now, the position of operating line, it gives us information about the driving forces between the liquid phase and between the vapor phase, right? So one thing that you have to understand, that if we have our rectifying section in the distillation column, the operating line is always below the equilibrium curve. You might have noticed when you are doing calculations for gas absorptions, or when you are trying to find number of stages, or height of transfer units, or number of transfer units, you might have seen that the operating line is above the equilibrium line. But in distillation, the operating line is below the equilibrium curve. Have you thought about that? What is the reason why the operating line is always above the equilibrium line in gas absorption? Why operating line is always below the equilibrium curve? In distillation, the reason is that vapor coming to any plate, they normally contain less of the low boiler, which is also called more volatile component. So the vapor coming to any plane contain less amount of more volatile component than the vapor in equilibrium with liquid leaving the plate, right? So if you if we go back, if we look at this picture, so the more volatile component, or the mole fraction of the more volatile component yn, it will be much more higher than yn plus 1. And this yn, for an ideal stage, it will be ye, or if the mole fraction in at the equilibrium, right? So the yn will always be greater than yn plus 1. And similarly, if we look at this yn minus 1, it will be much more than simple yn, because the mole fraction of the plate at the equilibrium will be higher than the streams which are entering to the plate. So vapor coming to any plate contain less of, or less concentration of, the more volatile component as compared to the equilibrium. So if you look at the driving force for the mass transfer in the rectifying section, the mole fraction of the vapor phase will be lesser than the mole fraction in the equilibrium. So the driving force will be ye minus yn plus 1. Similarly, for the gas absorption, the operating line must lie above the equilibrium line, because in the gas absorption, the concentration of the solute will be smaller in the below section as compared to the will be higher in the below section as compared to the above section. So the driving force will be yn plus 1 minus ye, which is the equilibrium. So this is the reason that operating line is above the equilibrium line in the gas absorption, and operating line is below the equilibrium line in the distillation column. And as the distance between those operating line and equilibrium line, they helps us in understanding about the driving force. So whenever we say driving force, it means the difference between actual vapor composition and the vapor composition at equilibrium with liquid, or any particular position in the equilibrium stage. Now I will discuss very briefly, and I think you have might have seen the operating line diagram for the gas absorber. So we do it quite similarly in the case of distillation as well. So but this is just to show you that how you can calculate the number of ideal contact stages in the gas absorber. So first you draw your operating line, you know the slope of the operating line, and then you know the mole fractions in the liquid phase and the vapor phase, and you have to find the outgoing for outgoing the mole fraction in the liquid phase and the vapor phase, and then you start putting your stages, and then you count them, number one, number two, and number three. So this kind of systems we have, like three stages or three ideal plates or three ideal number of transfer units will be required for a certain separation. I will show you a similar approach that we use in distillation. So I will show you a McCabe Thiel method, which is very easy to understand, and it will help us in finding the number of ideal stages or the number of ideal plates in the distillation column. Right. So that was about equilibrium stage systems, and there will be no assignment from this discussion. You will have an assignment on distillation. I will discuss distillation tomorrow, and the main reason for having this discussion was to just to build your knowledge on equilibrium system. What do we mean by equilibrium? What will happen to the streams that are entering to a particular stage, and what will happen when they leave the stage? It is very important that the streams entering a particular stage, they should not be in equilibrium, but the streams which are leaving a certain stage or a certain plate, they must be in equilibrium if we call it as an ideal stage. But normally, practically, we do not have ideal conditions, and that is why we have to consider the efficiencies of each stages and efficiency of plates, or like the way that we define our system. So that's why we include the efficiency. As the efficiency close to 100%, then we call it ideal stage. If the efficiency is less than 100%, then it means the actual efficiency of each stage and each plate. Right. So I would like to ask you that if you have any questions, if you have any questions around equilibrium state systems.
I have a question regarding the evaporation assignment A1.
Okay.
Um, shall we take that later, or can I take?
I will come back to that your question later, and because first I would like to ask everyone that if the discussion on equilibrium stage processes is understandable for everyone, or if you have any questions regarding that part, then I will come back to there is a question on examination, and then I will come back to your question on evaporation.
Okay, thank you.
Yeah. So first, I would like to ask anyone that who have any questions around the equilibrium stage operation. As I mentioned earlier, there will be no assignment related to this discussion, but this discussion will help us tomorrow when we are going to have more detailed discussion on the distillation column and distillation, and how we calculate the number of stages and number of the plates in the distillation column. And also this discussion is helpful for your understanding about the leaching system, about gas absorption, and many other equilibrium state systems. So there is no question on equilibrium stage processes. Okay, then I had a question about the examination. And the question was that if you still need to do a final examination even after you have finished your assignments regarding all different types of separation techniques. This year, we have changed the examination like from Solstenta to like home exam, and we have divided the home exam in terms of assignment on each particular separation technique, and you have been submitting your assignments for each technology like gas absorption, adsorption, leaching, and many others. And I have already put the assignment for evaporation and humidification, and then I will put another assignment on distillation and one more assignment on the drying. So when you finish those assignment, this is part of your examination. You don't need to give any final examination. So the points that you get from each assignment, it will be added, and then you will get your final grades in this course. So it is very important that you submit your assignments within the deadline, because if I remember, I have mentioned it very precisely earlier that if you submit your assignment after the deadline, even your assignment is 100% correct, you will not get high grades. So in order to get high grades, it is important that your assignment is correct and you have submitted your assignment within the deadline. Right? So all the points that you get from each assignment will be added, and then you will get your final grades. And I would like to ask that if anyone would like to have any question on the examination, if there is certain ambiguity or any clarification that is required from any one of you regarding the examination. No, then I have. Then, if anyone is willing to stay for evaporation, then you are welcome because I have a question around assignment number, like recommended problem number A1 for evaporation, and I will show the solution for that one. So, if anyone is willing to stay, then you can. Otherwise, that we are done for today's discussion, and then I will see you tomorrow. Right? Thank you.
Excuse me, I have a
Yeah.
question.
Yes. Yes. Yes.
Uh, my internet was breaking up a bit. Didn't quite catch all the info about the assignment. So if you're able to get a return if you do something wrong, or is it like you only get the one chance?
Okay, this is a very good question. So the thing is, the thing will be like this. Like for example, let's say if you submit your assignment for evaporation, right? So there might be a case that your assignment is 100% right, then it is gone, right? And then you will get your points for that particular assignment. But in case your assignment is not 100% right, then we will give you point. And if it will be like for example, if you would like to, like maybe I can rephrase it in another way. When you send in your assignment, all your points will be given. It will not return to you at that moment. So when we combine all the points from all the assignments, you will get your grades. But if you wish that you would like to improve your grades, then maybe we will give you another assignments in, like it will be similar to like re-examination, but you will not get your assignment back in this stage that you just revise it and send us back, and that it will be included in the final grades, right? So your submissions to each particular assignment will be final from your side, and you will get points from that particular assignment, and then all the points will be added, and then you will get your grades. If you feel that you need to improve your grades, then you can always go for a re-examination the next time when we have the re-examination, but it will be final for this. So this is quite similar to what you do in the examination when you have sent in your uh, answer sheet, and then it is gone, and then it will be for us that we will mark them, we will give them numbers and points, and then it will be counted towards your final grades.
Okay, thank you.
Right? Okay, good. All right, then I will see. I will see you tomorrow. Now I'm going to show the solution to the evaporation problem, which is recommended problem A1. So if anyone is willing to hang on, then I just share my screen. Let's see. Mm, no. Mm, where is the solution?
Hi, I have a question.
Yeah,
So if you don't have enough points on your final grade, to pass the course,
yeah.
how do you have like will you do another assignment to get enough points, or do you need to redo all the assignments for the whole course?
Ah, at this stage, I'm not sure. I might need to discuss this question with Jorgen. Um, but I think it's a good point. I will come back to you hopefully tomorrow or maybe the next time when we will see. Then I need to speak with Jorgen about this. That how we are going to have the re-examination. Will it be for only one assignment or for all of them? But I'll come back to you. But I'm not sure at this stage because I need to discuss with this with Jorgen as well.
Thank you.
Yeah, thank you. Okay, and I'm not finding the. Okay. Uh, okay, maybe I need to connect with my other computer. I will be back in 5 minutes, and then maybe you can reconnect to the same Zoom link, and then I will show you that the solution to the assignment A1. Right? So I will be back with my other computer. So I'm going to end the meeting from this, and then you can join it after 5 or 10 after 5 minutes from my other computer. Right? Then see you.